Hello, everyone. So we have James here, James from Google. So he's going to talk about the evolution of object-oriented programming. Hello, James. A bit
Hey,
about James is he's a nerd, software developers who share what he learns with others through presentations, blogs, demos, and code. After over decades of professional programming, he's now a self-proclaimed type pure functional programming zealot, but often compromises on his ideals to just get the stuff done as well. After spending too many sleepless nights in the data centers repairing red arrays, he now prefers high-level cloud abstractions with appropriate escape hatches. He is a huge open source proponent, hoping to never get burned by lock-in again. And I'll be sharing the James site as well, so you can go and take a look at more of his work. So thank you again so much. Over to you, James.
yeah, awesome. Thanks so much for having me. So this talk is going to be about the evolution of object-oriented programming. And so we're going to talk about changes that are happening with the ways that many of us have been programming for a while. And the one way that I like to look at this is that there's these cycles that happen in a lot of things, but today we'll be talking about it in terms of object-oriented programming. And the cycle often begins with finding limitations in some current paradigm that we have with how we're building things. And so for me, one of the first places where I experienced this was with Java EE beans way back. And one of the limitations with them was that they were actually pretty hard to test. And it was hard to be able to run unit tests against them. And so what happened was we developed new patterns and to deal with some of these limitations. So many of us started doing XML-based dependency injection with Spring Framework, and this allowed us to work around some of the limitations in the paradigm. But we did this really as library, just fully supported by libraries, not something that was actually changed the structure of the programming language in any way. So then what happened was annotations became a thing. And so we're able to now have language support that supported a new paradigm that allowed us to achieve the same thing that we wanted, which was making it easier to test and decompose our applications. And so with annotations and the support from the language, we were able to make this better. And so we can see these cycles happening in a lot of different places, and that's what I'm going to be going through. But to illustrate this, I'm going to just dive into some source code and walk through some source code here. So one of the first things that I want to show you that's changed in object-oriented programming, or is changing, is illustrated by a example application. So we're going to play a little game, and I'm going to run this application in debug mode. And this little application, what it does is it has an add1 function that takes an int and returns an int. So I'm passing it the int 2, and I'm calling it add1. So what do you all think the output of this is going to be? You are probably right. The output is 3. Okay, so now if we call that same add1 function again with the same parameter 2, what do you think the output's going to be this time? Now, you might think it's going to be 3, but you probably have figured out that I'm going to trick you, which I am. The output is actually 4 this time. So same function, same input, but this time we get a different result. Okay, let's play again. Add1, same output. What do you think it's going to be this time? You might think 5, but in fact, it's actually not even an integer, it's null. And let's run this one more time. And this time, oh, looks like our output from calling that function was actually an illegal state exception, which is certainly not an integer. So what's actually happening underneath the covers? Let's go look at add1. And you've probably assumed that I am playing tricks on you. So I take my integer and I have a global mutable value here that I'm updating, and based on the base the external state, that mutable state, I'm doing different things. So that's how I'm playing tricks on you. Okay, now let's play this game again, but this time I'm not gonna do anything to trick you. I've got a function here, add1, which takes a immutable value, an int, and returns a value. And so that value is just adding 1, as you would expect. So let's run this again. And this time, no tricks up my sleeves. We see that the output of adding 1 to 4 is 5. And if we call this thing again, it's going to be 5. And if we call it again, it's going to be 5 and 5 and 5 and so on and so forth. So this is based on full immutability. So everything that we're dealing with when we call this function, this what would be called a pure function, because it takes a immutable value and returns a value, and it's not talking to the outside world. So there is no outside mutable state like there was in the previous example. And so when we write our functions and our values like this with immutability and with pure functions, then we get to something called referential transparency. And referential transparency allows us to, at any point, substitute a function call with a given value. Anytime that we would call that again, we could actually just substitute that with the value that we already recomputed. So we can be sure with immutability and referential transparency that we can always do that substitution. Okay, so why does this matter? We certainly build a lot of programs that are doing state mutations somewhere, and so why does it matter that we want to try to prefer referential transparency? One of the big reasons for me is that I have found that it can be really hard for me to understand the flow of a program. Where is mutation actually happening when I'm using mutable state? When I'm using pure functions and immutables, then it's much easier to follow through a program and understand exactly where state mutations are happening. So this helps with debuggability, understandability of the program, and then also many of us are writing concurrent applications. So when we're writing concurrent applications, it's really hard to understand with mutation where mutation is happening, what thread it's happening on. State can change out from underneath you when you're not expecting it. And so with immutability, that can't happen. So we have better understandability of our programs and much easier ability to have concurrency in our programs as well. So those are just some of the reasons why I now really prefer immutability and pure functions and referential transparency for my applications. So immutability. Now today, pretty much everything I build is using immutable values. I almost never use mutable values anymore in any of my programs. So this actually does make some things more challenging though. And so let's dive into the next piece of this, which is looking at builders. So we in the Java world, we started mostly preferring immutable value objects, DTOs or value objects, to represent our data structures. I'm actually going to go to the vehicles builder. And so this is a vehicle, and a vehicle has these immutable fields on it. So I've got my name, my number of wheels, my default number of wheels. Maybe I have a number of cylinders and a default number of cylinders. And so this is good. This is an improvement over the way that I used to do things with mutable values. But constructing these objects turned out to be kind of challenging. It's weird that in object-oriented programming, object construction turned out to be one of the more challenging things that we had to tackle. But so great, we've got immutable values. But if we want to use just constructors to construct my vehicle, now I need to write a bunch of code to handle all the different variations, the different defaults, and you can see here's all my different constructors. And this just isn't worth it. It's too cumbersome, too painful to write all these constructors so that I can get a concise syntax for assembling my immutable vehicles. So the pattern that emerged was builders. Builders, what they did was they said, okay, let's have a mutable thing that we can do these default values on and allow people to override the defaults. And so this makes the ergonomics of creating an object easier. So in this case, I have a way to set the number of wheels, a way to set the number of cylinders, but I've got my defaults. And so we're doing this mutation in the builder, and then we call .build, and that's going to then assemble our vehicle with those parameters. So we get to our immutable object. So this was an improvement over trying to use constructors for this type of thing, but it has some challenges. So when we get into more complicated structures, like an owner that has vehicles, now we get into some messy pieces where now we need to deal with, let's say we have a list, an owner has a list of vehicles, and we need to have a way to update a vehicle. The ergonomics of dealing with these builders gets kind of tricky, because at some point we need to probably modify something down in the tree of our object structure. And so then we have to be able to go back to a builder. And if we've got a list, then what do? We got to find the thing in the list that we want to mutate, and then turn that into a builder. And it just gets kind of tricky to deal with these larger, more complicated structures, and going from builders to our immutable objects and back and forth, and traversing down trees and all this kind of stuff. And so there's some new patterns that are emerging to make object construction and mutation on immutable data structures easier. So in Scala, this is called a case class. And so with a case class, what we do is we just define the parameters on a class, and we can set defaults on that thing as well. So here I can say my default number of wheels is 4, and then I've got a maybe number of cylinders, which is an option, and I can have a default value for that as well. And then I can have an owner, which has my list of vehicles on it. And now we can create our vehicle. Now this is immutable, so I can't call Cadillac .name. It's an immutable value, so it's not going to let me do that. But now I've got this nice ergonomics for creating instances of my vehicle. I can just call vehicle, give it a name, or I can give it the number of wheels or the number of cylinders. There's also new language features that are emerging in a lot of language to do the ability to do named parameters. So in this case, what I'm doing is I'm saying, all right, the name is equal to Cadillac, but then I just continue on to my, I set the number of cylinders, so I can use the name parameters as well to construct my vehicle. So default and name parameters gives us a really nice syntax for how we can create our objects. Kotlin has something similar to this as well, called data classes. But there's a challenge still of, all right, I've got my immutable vehicle. Now I want to be able to mutate one piece of it. And to do that, the copy method on a case class in Scala or data class in Kotlin allows us to then use name parameters to set specific properties. And so now this will create a copy of that object with the new parameters set on it. And so nice ergonomics there. But when we do get into those trees of objects, there is some challenges with how we go down into a nested structure and just make a copy of something deep in the nested structure and return the new kind of outermost structure with just that one mutation that was down in the tree. That still can be challenging with immutable objects, and even with these constructor name parameters and default values and the copy methods. So there is a new pattern emerging, and this hasn't quite propagated into kind of the next phase of that evolution where this is kind of well supported and we all kind of agree on a solution yet, but it's called lenses. And I'm not going to go into a whole lot of detail on this one because it gets a little crazy, but essentially what you can do is create a query that queries down into a deep nested structure and allows you to create an immutable copy down inside of that based on where your query got to down into that structure. So lenses are kind of, I think, the next part of this evolution for dealing with mutations on immutable data structures. Okay, but default values and name parameters allow us to have a lot better ergonomics for how we define our classes and deal with them without having to use builders. Okay, so that is for constructing objects, but there's another thing that is emerging that allows us to create not these things that hold data, but taking functionality. So essentially functions, pure functions that take input and return an output, and always do that for the same for any given input, and allows us to combine these things together. So in this case, what I want to do is I want to be able to have a filter function, and I'm going to do a filter function that says, all right, is basically this even? Is the number of cylinders even? And another filter function that says, do we have more than 8 cylinders? So those are my two filter functions that I'm going to use, and I can apply those based on, so I can take my number of cylinders and apply that filter, that predicate there, balanced or beefy, but we want to sometimes be able to combine together these functions and be able to create new functions, which are the combination. And so one way to do that with a predicate is I can take my balanced predicate, that function that checks if it's even, and I can say, or, and then give it another predicate. And now I have a new predicate that is the combination. This is why this is called combinators, that combines those two things together. And now I can use my balanced or beefy predicate and run that on my number of cylinders. So combinators allow us to create new things, kind of like we saw with the case classes. But in this case, we're creating new things that are just functionality, so not the actual data. Okay, so combinators are another pattern that is being used pretty widely for creating combined functionality. Okay, so that's our combinators. Let's continue on now to the next piece of evolution that we're seeing. And this one is called algebraic data types. So algebraic data types are a way to represent data and using algebraic laws and information. And so the first algebraic data type that I'm going to go over is typically called a product type. And so let's say that I have a type A and a type B and a type C, and those now in my example are just Booleans, but could be anything. And I want to create a data structure which combines together, it ands together an A and a B, for instance. Well, I can create a data type called a pair, and this is now over in Kotlin, and a pair is actually just a built-in data type in Kotlin. And so I have a data type that allows me to combine an A and a B together. And so I can also use a triple data type, which is also built into Kotlin, and that allows me to combine 3 different types together. So that's an algebraic data type for representing anding together multiple types. So it's also called an intersection type or a product type. When I'm using a pair or a triple, there's another name for these in other languages that have out of the box support for this concept, which is called a tuple. And so this is just a anonymous way to combine together without a given name to this thing, multiple types. So we can also do this in Kotlin or in Scala using something that you've already seen in Scala, but in Kotlin we can do a data class, and I can give this A and a B a name. So maybe I want to call this A and B. That's a terrible name, and then I can put in here an A and a B. So now we have a name for this thing that is a combination of these things. And so this is just another way to represent a product type. Okay, so the more interesting ADT, algebraic data type, that is emerging in a lot of languages now is called a sum type. And a sum type allows us to do an OR. And so this is an algebraic OR. And so this says, I have a type that is either an A or a B. And so this is the either. We typically call the left value left and the right value right. And then you can also do or with many types. So let's say you wanted what I'm calling here a trither, and a trither can be an A or a B or a C. Then I've defined my trither, and now this has a middle value as well. So this is also called a sum type or a union type, and it is taking types and oring them together. And this may look a little bit like an enum, and it definitely holds some of the same traits as enums do. So there are some languages that now have built-in support for sum types. In some languages, we can simulate sum types using inheritance. And so in Kotlin, what we can do is we can say I have a sealed class called an either, and then I have a left which inherits from either, and a right which inherits from either, and the value of a left is the left side of the either, and the value of the right is the right side of the either. And because this is a sealed class, no one else can implement this either. So I'm guaranteed that I'm only ever going to have a left or a right of this. And then you can see the trither implementation. Okay, so this allows us to have a data structure which holds either an A or a B or a left or a right, and that's the either or trither. You could do this however you want to. So let's look at why this actually matters. And to do this, we are going to actually create a left and a right. So I've got my either left, and that, let's open this up a little bigger. I've got my either left, and that has a value, which is, you'll see that my left side is a Boolean, my right side is a string in this case. So if I give it a left value, then that has to be a Boolean. So there's my true. And then I've got my right, which is just has a string in it. So where sum types are really powerful is with pattern matching. So with pattern matching, and this is in Kotlin again, so what I can do is I can say, all right, when, and I'm going to give it my either type, so I could put in either the right or the left type in here, and then there's some type inference weirdness there, but if I've got my right value in here, then what I can do is I can say, if this is an either dot left, then you'll see this is highlighted green in Kotlin. The reason why it's highlighted green in Kotlin is because it is now smartcast that value. So it's smartcast it and knows that now it's an either dot left. So now I can pull the left value out. If it's an either dot right, then I can again smartcast it and get the right value out of that. So there's one thing cool with these sum types in pattern matching is that if I try to comment out the other case here, then I actually get a compile warning in Kotlin, and you can turn this into a compile error. But the compiler actually is going to tell me, hey, your pattern match is not exhaustive. You haven't actually handled all the possible cases. And because that's a sealed class, it knows what all the possible cases of that thing are. And then likewise, because I've matched and said this is an either dot left, I can't do r dot right on this thing. It's like, hey, r dot right doesn't have a right because it's not a right, it's actually a left. Okay. So there's one of the interesting things that we can do with these sum types is we can essentially replace what we've done a lot of times with the visitor pattern. And so I'll give you the link to the source code for all this, but there's an example here that uses the visitor pattern in what you're probably used to in Java, and then uses instead ADTs, uses sum types and pattern matching to do the same sort of thing. So one of the nice things is being able to separate our data type from the functionality on that data type and essentially replace what we typically do with the visitor pattern there. Okay, so that's our sum types and product types and pattern matching. Let's now move on to the next thing, the next piece of evolution I want to go to, which is called adhoc polymorphism. So let's take a look at an example here. So the polymorphism that you're probably most familiar with is inheritance-based polymorphism. Inheritance-based polymorphism says that if you want shared functionality across a set of different types, then what you do is you extend those types to inherit that functionality. And there's another way to do polymorphism, which is called ad hoc polymorphism, where what we can do is add functionality to types by doing an extension method on that type. So here in Kotlin, what I'm going to do is I'm going to add functionality to an iterable of char. Its name is sum, and it returns a string. And I have some logic there to sum up an iterable of characters. So now I've got my list of characters, and now I can just call the sum method on it. So I've been able to add functionality to all iterable of chars in this way. And so that's nice. I'm able to kind of cross-cut that across the type hierarchy and add functionality to things. I can also do an iterable of string and add a sum to that, and you can see that that works. But there's another way to do this, where what I can instead do is I can say, all right, I've got this abstract class, toChar of t, and now I can create implementations of things like a toChar of string and a toChar of char. And so now I have implementations for a string and a char. And then what I can do is create an extension method called sumT on my iterable of t. So now I'm combining together generics and extension methods. But my sumT needs to know how to convert to a char. And so what I need to do is take a toChar of t here. So that's my implementation for how I actually do that sumT. I use the toChar to convert it to a char and then can do my summing on it. So that's great. Now I can create a list of char, call sumT, and pass it my char to char, which we defined up here, or do the same thing on a list of string. Okay, but what if I want to be able to call my sum on a list of char or string? So then I have another thing, which is my iterable toChar takes my toChar of t and returns a toChar of iterable of t. So the way that I can use that is now I create my list of string of char or list of string, and now I can say, all right, let's call sumT on my iterable toChar, but then I have to give it my char to char. And so you can see that this starts to get a little unwieldy when I'm operating generically on things that need to have some context about how to convert from one type to another. And so this is great. The ad hoc polymorphism is a great step here. But there's another concept that I want to show you, which is called type class, typically called type classes. And there's another name for it in Rust, actually, and I'm going to show you Rust. I forget the name of it. But type classes allow us to be able to fill in those parameters. The compiler will actually find the thing that exists and can fill that parameter in so that we can have these converters, but we don't have to explicitly tell the compiler where to go find the thing. And so this example is just like the one before, but this time implemented in Rust. We could also do this in Scala because it has support for type classes. But let me show you how we actually use this. So I've got this sum method that's going to take a vector, in this case of char. And our sum method, what it does is it says, I need a toChar of t. I need a toChar that knows how to convert a char or a string. And so you'll see that here's my toChar for char, here's my toChar for string. So I've created those things that know how to, in this, when I call the sum method, know how to get this toChar for the t that was passed in. And so here, this will work fine. I've got my sum on a vector with chars. Here I've got my sum on a vector of strings, but I also have a toChar for a vector of t. So that allows me to do a vector of string or of char. Let's go run this thing so you can see that it actually works. So there we go, cargo run, and you'll see that it all worked as expected. But now if we go in and let's say change our chars here to integers and try to go rerun our cargo run, you'll see that now Rust is actually telling me, hey, I don't have a toChar that's implemented for integer. And so the compiler is filled in, it's figured out, hey, you need a toChar of the type that is in this vector, and you don't have one for integer, so it's a compiler. So this is called type classes and is part of ad hoc polymorphism. Okay, so that's our example there for type classes. Let's go on to one last example, and then we'll wrap up here. Okay, so I've got a Scala example that kind of combines together all the concepts that we've seen already. So in this example, I'm going to do JSON parsing, and I want to parse into a vehicle, which is the case class that you saw before. And so to do that, I'm going to build up using combinators some functionality to do validation of my JSON. So I'm going to verify that the first letter of the name or first letter of a string is an uppercase letter. And then I'm going to use combinators to make sure that the minimum length of this thing, and keep is the combinator, or the way to allow us to combine this with another one. So I'm going to say, and it also starts with an upper. So now I assemble my JSON parser, and this is where I'm using, starting to use type classes, because I've got a read int, and you'll see that a parameter to this read int is I need something that knows how to read an int. And you'll see that I didn't specify it here, because Scala and type class support is actually able to pull that out of my default JSON parsing, and my default JSON parser has something that knows how to read an int. And so that's using type classes. And then you'll see I'm constructing my vehicle here. So when I actually get my parse result, I can construct that thing. Okay, so I've got this block of JSON here, and you'll see that my name is just a V. So if I go run this thing, let's go run it, then we'll see that when it tries to run that parser, it's actually failing with some errors. The minimum length didn't meet the 2 expectation, and it didn't start with an uppercase character. So let's go back and put in another name here and rerun this and make sure it works. And I want to show you one other piece of this where I'm using ADTs. So there we go. Now we get our vehicle assembled. Okay, so when I call JSON.parse, give it that JSON. When I call validate, you'll see that, again, it's using type classes to pull in the thing that can read a vehicle, which we defined up here. And then you'll see that the output of result is actually a sum type. A JS result is a sum type that can either be a JS error or can be a JS success. So then I use pattern matching and say, all right, if it's a JS error, then we're going to call the print errors function, give it the error. If it's a result, then we just print out the value, which we saw there. Okay, so JSON parsing turns out to be a nice way to combine together the immutability. All this was immutable. Combine together the combinators, which we used for our JSON validation. Combine together our ADTs. Combine together our ad hoc polymorphism with type classes. So we saw kind of all that stuff coming together into an example there. Okay, so that is some of the stuff I wanted to, or that's all the stuff I had time to show you for the evolution of object-oriented programming. And I think we might have a minute or two for questions, and then I'll also be over in the spatial chat to answer more questions there.